Okay, so thank you so much for coming to a Sunday to my tutorial. I hope after lunch I will not get you to sleep. So I divide my talk in four parts. So the first part is introduction, second part is Metaheuristics, and the third part is in Iterated Local Search, and then I have maybe if I have time some practical issues. So let me introduce myself. So my name is Helena Ramalhinho Lourenco. I'm Portuguese, but I live in Spain, Barcelona. And so you see, Portuguese have a lot of last names, and we can choose which one we want to use, basically. So there's a big mess. So before I moved to Spain, my last name was Lourenco, but then in Spain, they never recognized me as Lourenco. Even one time the director said, I cannot give you tenure because you don't have any publication. So I panic. And so then I decided to use my mother's name, which is Ramalhinho, is my mother's name. It's very unusual name. Lourenco is very normal, like Mrs. Smith. You know, a lot of Lourencos in Portugal, but Ramalhinho is only my family. So I said it was a nice opportunity to use my family last name. So I have a degree in applied mathematics from the University of Lisbon. Then I did a PhD at Cornell, and then I moved to Spain because I married a Spanish man. So that's the reason it's a good reason, right? So I'm in Barcelona in this university. I put some pictures of me. I like to people know me. I love tennis. So today I'm a little bit in panic because I cannot see the final of the Open of Australia where is a Spanish guy playing. So I cannot connect to my server in Spain. So I'm a little bit upset, but that's okay. I went to all the Grand Slams in my life, so I fulfilled one of my dreams, which being all 4 Grand Slams. It was my dream. I get someone from Melbourne to invite me during the Grand Slam, so I almost convinced him that I will do the teaching free, everything free, if I can go to Melbourne during the Open. And I also like to do safari, so I've never been in Cape Town. My first time in Cape Town, I love it. But I've been a lot in Namibia, Botswana, Johannesburg, Kenya, because we love to take pictures. And so we'll have to come here. About the university, Universidad Pompeu Fabra is a public university. It's the newest one in Barcelona. It's a university that was created in a very different way. We teach a lot in English and we are worldwide. So any person from anyone in the world can come to university, and this brings them to be really, really the top university now. Is #1 in Spain, and it's also very well positioned in Europe and in the world. So because we teach a lot in English. Even we used to have a scholarship for women from Africa. I have to check if they still exist, because we have a scholarship it's a Kenyan woman called Dorcas Mutoni. We give them like a really important recognition because she's very important in computer science, and we have. So I will check this and we'll let you know. And also I'm the director of the Business Analytics Research Group. So this is a group that has people from marketing, from statistics, from computer science, and from operation research, and we try to really solve real problems. So we're really interested in real problems. Okay. So my talk today will go on a gentle introduction to operation research. So after a funny, this will be easy. I will do very fast. And then I will go on the metaheuristics. What is the metaheuristics? I think I don't see it. Oh, yes, the metaheuristics algorithms, iterated local search, some extension, and then some applications. In reality, these two, I will do it together because I will explain one metaheuristic and one iterated local search and one application. So I will do it. Okay. Of course, you can interrupt me whenever you want. Portuguese have a really big problem. We speak too fast. We speak so fast that Brazilians cannot understand us. We speak Portuguese too. So I tend to go like very fast. And I know I always say to my students, please stop me, because I go like very fast. Okay, so you all know what is operation research, but I want to remark, this PowerPoint is to remark that operation research was born to solve real problems. And it's still true. I mean, we need to solve real problems. So this is very important. And I think we can make a really big impact in the future. Here I put a definition of analytics from Informs, which I like very much. 20 years ago, people were here. getting data. Business were worried about getting data, getting BI, getting data. Now they are on the machine learning phase, the predictive. And this is come next. So that's what operation research are really important. So, okay, I have this data, I did this forecast, what you gonna do about it? You're gonna hire more people, you're gonna buy more cars, you're gonna put more warehouses. So I think only a few companies are in this phase already, special big companies, but they will arrive a lot of here. So most of the work we've done is here in the prescriptive analytics. And I also like to put this PowerPoint a lot when I do tutorials and when I do courses, because this is really what we do. Now we are here solving real problems. Of course, to solving this problem, we need to know the theory, we need to know the models, we need to know the algorithms. So I always try to go here to when I'm more theoretical students, and here when more application. But the main objective is to help to make a decision. That's the main objective of our work, in my opinion. Okay. So modeling is very important, because even I'm going to represent you algorithms and metaheuristics. The modeling helps you, I think, I heard this this morning, helps you to really understand the problem. Because if you don't understand the problem, you cannot solve it. It's very important to understand the problem very, very well. And modeling helps you to structure the problem very, very well. Some people jump to the algorithms immediately without understanding the problem, then the solution is not useless. It's useless. It does not help anything. So modeling is very, very important. Model simplifies the reality. It really is a simplification. That's something that also we have to understand. So if you're going to buy a house and they present you with the plan of the house, you can see where is the kitchen, where is the bathroom. This is modeling. It's not the reality. But it helps you to understand what the house is, right? So this is the same. We cannot put everything on the modeling, the reality, because we cannot solve it at all. We only buy the house after we see the house constructed with all the decoration, everything. So no, but the house, the modeling, this plan of the house helps you to understand. So we have to balance this between how much reality we put in the model, how much reality we leave outside. Okay, there's something I will explain now, so that then using some other techniques, we can incorporate things that we leave outside the model, but will help us to make the decision. So, and after the model, of course, I'm going to focus on yeah, it's like in the white thing, it does not appear. That's okay. So,
change the background of the slides.
That's okay. Disappear.
The white background.
That's okay, don't worry. So then after doing the model, we're gonna, that's the focus of this tutorial, going on the algorithms. How do we solve it? And then we have to put this on reality. So think about that. My work basically is on solving real problems. Okay, so the algorithms should be really efficient. And do they need to be optimal? Yes and no. Okay, so if you can get the optimal solution, maybe it's good in some situation. But if your data is stochastic, what does it mean, the optimal solution? So this is discussions that are really interesting here. Also, they need to be efficient. So if someone comes to me and say, oh, I need to solve this problem, and I need you 30 seconds because I have my customer in 30 seconds on the phone. And I tell, no, I need at least 45 hours. Okay, so say, okay, Helena, that's nice work. The university it's useless. So the time is important. So there's some situations we can go to the optimal solution. We have a lot of time, and some situations we don't have the optimal, we need the optimal solution, and we don't have time. So this is a tool. You need to really get the best tool. And another thing is when we have stochastic data. What happens after the solutions? You need to think about most of the problems we solve. Someone has to make the solution. Someone. So the solution must appear somewhere. It could be in a very intuitive way, very simple. It could be using an algorithm. But these solutions have to be given to someone. So this is really interesting to design the algorithms. Of course, you see all this on linear programming, TC parameters. I say the modeling, the optimal solution is really important in some situations. I work a lot on combinatorial optimization problems. So combinatorial optimization problems, remember very well, is when we have a set of elements and the solutions is subsets of these elements. And you have to choose the best subset of these elements. So this is the case of, for example, the TSP, the vehicle routing, location, scheduling, click, something that I will explain. So these are all combinatorial optimization problems. That's most of the focus of the work we do. Okay, so just, I know that you see this, some of this in the morning. So very briefly, I review these ones. So the vehicle routing is very popular. It's one of the most popular ones when you have a set of customers, you have a set of warehouses, you have to distribute things. So for everything in e-commerce where you cannot download by your computer. And I used to say, my students think that everything can be downloaded by the computer. Music, maybe, a travel ticket, maybe, but the jacket, the shoes,
even downloaded on the computer, because you want the optimal routing for the data as well.
Yeah, you need a computer, but
the network routing on the computer is also optimized.
Exactly, optimized. Exactly, that's correct. Exactly. But you think they used to buy online on Amazon and all this things. The things that say, you know, the things don't appear. They still don't appear at your house. Maybe. Oh, but we have 3D printers. Yes. How do you put the material on the 3D? Okay, if you want to cook, you need the rice, right? So, and if you look at the numbers, the e-commerce for physical things are much bigger than for things that you can download, much bigger. Okay, so the vehicle routing, you have to minimize. So a lot of vehicle routing, vehicle routing probably is one of the most popular because you cannot solve it for many, many things. Then you have facility location. I think this once you see this morning too, I saw it that you have to location some facilities, you have some conditions, so what is the best location? So we have several problems that the P-median, the covering, the capacity facility location. This is another very popular. Then we have scheduling. Okay, scheduling, it's lots of things in scheduling. Scheduling is complicated. From the three that I present so far, I think scheduling is the most complicated. Because when you change something, you can destroy the scheduling completely. Okay, so facility location, if you locate one place here, if one is bad located, the other maybe it's good. But in scheduling, as soon as you put something, you can destroy everything. So scheduling is really complicated. Okay, ask the people that do course scheduling in universities or exam scheduling. Think that this is very complicated. Okay, so I did work some company for scheduling. The thing is that if you get a good scheduling, that impacts a lot on the life of people. If you get a good course scheduling for students and professors, they are very thankful. Okay, so this is because it's really can be really, really important. And then there's one that I will also present, that I want to present a real application is Click. Do you know Clicks? So this is, I think you see the other three. Clicks is an application that uses a lot on social network and marketing, bioinformatics, chemistry, but this is the two that I use more. So what is a click? So give me, this is the definition. So I'm going to give you what is a click here in the picture. So I give this, so then you have the PowerPoint, but I'm going to explain it here. So you have a network, you have a set of nodes, a set of edges. A click is a subset of the nodes that are fully connected. We are a complete subgraph. So here we have this tree, okay, and they are all connected to each other. So it's a subset of the nodes that are completely connected. And they have an edge between all these pair of nodes. This is a click. Okay, so we have the Massim weight click that you want to find the click with the Massim weight. You can find here the Massim click, the subset has more nodes. Okay. And here you want to have the same, the subset, they have more nodes, but with a weight. You have a more weight. So we have weights. Here you can have weights on the nodes, but here we have put example weights on the edges. So this click as the one who has more weight. Okay, because you have weights. Okay, so this is another combinatorial optimization used a lot for social network to see who's more influential, which set of people have more influence on the network. It's also, I have one colleague which is fanatic from football, soccer, and it's also used to see who passes to who, okay, which are the most connected players. A Muslim cut click is different. It's like you have to have a click. So this is a click, but instead to have to look at the weight or the connections inside the click, you wait the ones who have the borders. So for example, this click has 2, this click here has 4 nodes, but this one has more edges that crosses the border, that have 1 node in the click, 1 node outside the click. Right? So for example, this 4, this 1, 2, 3, and 4 is a click, but I don't have 1, 2, 3 connections outside. This one has only 2 nodes, but has 1, 2, 3, 4, 5, 6, and 7. So if I influence this 2, I'm influencing more people. Okay? If I influence these 4, which is more expensive, because imagine I want to pay them something, I will influence 3 more people. Okay, so the max cut click is another problem that we are working for marketing. I will explain later how we create an iterated local search for this. Okay, and then you have a lot of applications. So you know this already, lots of applications everywhere. Okay, so everywhere we have applications of this kind of problems. Here are some examples that I will explain later. And some of the applications, of course, in the VRP, planning distribution, routes, picking, so optimizing the picking. It's another example that will explain how to picking inside a warehouse. You buy online for Amazon, someone has to pick your products. You know what picking is? Picking is when you go to warehouse and pick the things. That's picking. You get the things from the basket. So if you buy on grocery online, someone has to go your rice, your milk, put it in a basket and then take it to your home. This is the picking, okay? And then some of the examples here. Just to give you, I'm working lately very much on healthcare and social care. That's most of the examples I will give you on my plenary. Because if you think about in health, so in logistics, in retailing, in manufacturing, they've been around for many, many years. In health, just recently, last 10 years, people start to realize they can optimize things. And it's very complicated when you talk about optimization to doctors. It's very, very difficult because what are you going to say to me? You optimize, this is life of people. I mean, it's not a box, it's not a car. So we have, one thing that I will later say is that we have to learn how to talk with doctors. If you go to the social care, there are people that take care of other people, it's even worse. And I will explain some stories later. It's even worse because in manufacturing, in logistics, in retailing, in production, there's a lot of engineers. So we speak the same language. But when you speak to a doctor or a social worker, they don't speak your language. And they get offended if you say something wrong, which I think in a way they are right. It's because I'm going to optimize you only have 2 minutes for each patient. Okay. In 2 minutes, I cannot even understand what this person is. Okay, so we are working with them. I will explain some home care planning. It's very funny, the home care in Europe, only a few countries have very good home care. One is the Netherlands. I did present a project from home care in Spain. They say, no one wants to care home care. Comes the COVID, home care. Right? So now they are talking a lot about having, so for example, if you go to a hospital, you have a small surgery, you have to stay 2 days in the hospital. If you have a good condition at home, they're sent at home, which is better for the person. It recovers faster, less risk of infections. So this home care is becoming very important. So we're working on that. I will not talk about this optimization kidney exchange programs because this is another one. It's kind of going in Europe a lot too for the kidney transplant. And this is also a lot of optimization here, and it's very complicated. But we are looking in home care and social care. Of course, in transportation, we have a lot of things where to locate the electrical charges in the city for electrical, because the mayor of Barcelona is talking about, oh, everyone should have electrical car. First, the electrical cars are very expensive. Then, if at night everyone plugs the electrical car, the network will, I know what happened. And then, I mean, there's no, I mean, most of people don't buy electrical cars because there's no places to charge them. It's a very few places. So it's really interesting problems here. Of course, supply chain is also another one that it's really, we're going to have, we are talking also about humanitarian logistics. We have some projects with some of my colleagues in humanitarian logistics. And of course, manufacturing. So manufacturing is like a classical one. Okay, you have cutting and packing problems that you saw this morning too. Okay, the clicks are mostly, we present a lot on marketing. Marketing is another area where there is no much optimization. In reality, we did a paper. The paper got rejected because the referee said this problem is highly combinatorial, and you cannot solve it for more than groups of three. And it's like, come on, a minute. This is exactly what we can do. So the referees didn't understand the paper because they said they can only solve with groups of three. If you go more sets with larger groups, it's impossible to be solved. And not really. So it's really fun. And lots of applications in finance. I mean, sports applications are that my students like a lot too on scheduling for sport. So okay, so to conclude this first part is like, okay, working real problems. I think it's going to be the next boom. And so now everyone asking, are you doing machine learning? Yes, I do machine learning. Don't worry, because it's the name that the companies, some business know. They have no idea what machine learning is. I can guarantee, because some businesses, because I asked them and then they just thought this was fancy. Even I think machine learning is great. I mean, don't confuse me. But I think the next one will be that one, because we need to get value and insights. That's why I think what operation research people need. We have the data, we have the problems. We need to get value and insights to help people to make decisions. If you do this, you can put a face that they don't understand what you talk and they call you for everything after. So you come from one stage to the other stage. Okay, so this is the first part. Now the second part, I don't know how much you know about metaheuristics. How much you know about metaheuristics?
Too much.
Too much over there? You can go for a coffee. Or you can teach the course. Okay, so I'm going to talk metaheuristics, so then I can explain the iterated local search. So what is metaheuristics? So this is some of the metaheuristics I'm going to talk briefly. If then you want to know more, I can give you all the papers. There's a lot of things published. It's not new, this topic. Okay, so I like to put the citation one of my favorite writers, which is the Portuguese one. It's like, we need to act with methodology, with some method, and with discipline. And this is for the same for the branch and bound, the same for the metaheuristic. So we need to have like a structure, and that's the structure I'm going to explain to you. What is the structure of this algorithm should have to be able to get decisions? Okay, so in operation research, there is usually two big groups. People that are here in teacher programming exact method, people that are here. Most of them are tools. So you need to know which tool is better. So if you want to hang a picture in your house, you need to know to have the right tool, because if you get the bad tool, your all will be all destroyed, right? So this is exactly the same one. So I like to speak both languages. So in the metaheuristics local search method, we have all of this. I will talk about this, mostly this one, but the other one something. I will give you the idea. And of course, then on the solution on the exact methods, you saw the tutorial this morning. We see very nice solutions, the cutting. I remember you heard about the cutting. So these are very good solutions. So both of them are tools. You need to know which is the best tool, okay, to solve the problem. Not that one is better than the other one, no, for my opinion. Okay, what is the difference? So here you have very good methods that provide very good information, characteristics about the problem. You can get the solution is optimal, so you can convince your boss that this is the optimal solution. You cannot get better. That's it. Okay, so this is a good advantage. But here is that the running times is very short. So if you have a very short running time, this is very good because this can take hours, even with the best softwares in the market. Right? It can take hours or even days. It's easy to adapt. That's another important thing for business. The problems are alive. It happens to me. I start working in the problem, constraints, objective function, and then suddenly everything changes. The objective change, these constraints are different. So if you have to restore, so I used to say that the best algorithm for the TSP took 50 years to be developed. These people work on this algorithm is the best for the TSP. But now I say, oh, I have the TSP with time windows. Oh, so this is a little bit different. So this is easily adapted. So this is for especially also consulting companies is important because they can recycle their algorithms. And then it provides very good solutions for very complex problems, very large and very complex problems. Okay, so both of them are advantage and disadvantage. Of course, I cannot guarantee optimal solutions on the first one. That's the drawback. If you want to have an optimal solution, so far, no one could prove that the MetaHeuristic get an optimal solution. Okay, so the difference between heuristics and metaheuristics is, here is the formal definition. But the metaheuristics is, heuristic is something that constructs the solution. So if you want to do your course scheduling, we start with your course and put it in the best time. And then the professor that you don't like at all, that you put it on the worst time, right? So you do, so you construct this one. This one's, it's just like a process to finding good solution by really running several times several heuristics and guiding the solution. So here we start with the solution and try to improve it. Okay. So I've been designed basically the name of MetaHeuristic come by Professor Fred Glover, who invented the taboo search. He was the one who named it this MetaHeuristics word. Okay. So you can read this word. So it's really usually and implementing a simple metaheuristics, it could be very fast. You can implement the metaheuristic very fast. Maybe it's not the best, but you can run it in a very few couple of days. How to measure if a metaheuristic is good? Of course, there's no theoretical proof that it obtains optimal solution. So you have to do tests and look at the accuracy. So usually what we do is get, like for the small instances, we get the optimal solution using branch and bound, branch and cut for small ones and compare with the solution for the metaheuristic. If it's very close, the metaheuristic is good. Right? If the metaheuristic gets very good solutions, it's because it's good. Of course, for the large instances, you cannot compare because usually for large instances, we cannot run the branch and bound and branch and cut. So accuracy is important. Speed. Okay, one of the advantages of metaheuristic is that you can run it in very few seconds. In a few seconds, we have a solution. So if the metaheuristic takes as much time as the branch and bound, the metaheuristic is really bad. Because the idea is that we have solutions in very fast time. Another one that I like is simplicity. Easy to program. You don't have to control a lot of parameters. You don't have to do a lot of tests. If it's simple, if one metaheuristic is simple than the other one, so this one is better. The simple is better. Another one is flexibility. It's easy to adapt. I have an algorithm for the traveling salesman problems. I can adapt easily for time windows. I can adapt very easily if I have more trucks. I can adapt more easily if I have several warehouses. If I have two different products, one with different temperatures, like for example, in the soup and grocery, now you have three temperatures. Right? So these are the way we measure. how good is a MathILS? If you see a lot of papers focus on this one, which is okay, it's one of them, but these ones are also important. Okay.
Sorry,
Yes.
you said you can, for small cases, you can do branch and bound for accuracy. How do you test accuracy for large cases?
For large cases, you cannot.
But not test accuracy.
Sometimes you get a lower bound, but usually the lower bounds can be very far away. Okay. So, for example, one of them, the lower bound was so bad, and so we put it in a server. We leave it for 1 week running on the server, and finally the solution, we have an heuristic as like it was 3 trucks. It was the term of trucks, and the solution came the lower bound because we didn't find the optimal solution was 12.8. So 12.8 could not be real. So we know that 13 was optimal, but for largest cases we cannot. So, and usually this is done for theoretical for publish, because the business really don't care, because if you in business you compare with what they do with what you do. So even a simple heuristic usually is better for largest cases because they yeah. Okay, so for really complex problems that change a lot in reality. So I will explain. So for example, the routing for e-commerce, I mean, they run this routing for many, many trucks. I don't know here in Cape Town, but Amazon distributes about 30,000 packages a day in Barcelona. So we need a lot of trucks. So we need, the complexity is really large. So they are really interesting for this kind of problems. We have to have different scenarios, but you have to really adapt very fast, because that's the advantage of the MathILS compared with exact methods. But remember, I mean, most of them are tools. So, okay, so this is only the advantage. It's easy to implement. You can recycle some models very easily, and usually they give very good solutions in very short time. That's what I'm trying to explain to you. Okay, so these are the sum up. I'm going to brief now, and then I will focus on the iterated local search, which of course is my favorite one. Okay, so the first one is local optimization. So local optimization has been used for many, many years. And the idea is to find a local optimum. Okay, so you need to define a neighborhood, and find the best solution in this neighborhood. How do you construct a neighborhood? Using a move. This concept of move. Move is a small change you do in the solution. You do a small change. The solution is say every solution that is obtained after this small change is a neighbor. And now I choose my best neighbor. And I keep doing this until all the neighbors are worse, so you have a local optimum. Of course, local optimum is not a global optimum necessarily. Then you are lucky, you get it, but it's pure luck. Okay, so you have a subset of feasible solutions. You define a small modification. You construct all the solutions that are obtained through this small modification. This is the neighborhood, and then you look for the best neighbor. Okay. What is this small modification? So let me give you an example here. Oh, I have it here. So you know the traveling salesman problem. Everyone knows the traveling salesman problem, right? So you have to find this set of cities. You have the cities, you have the distance. You have to find the tour that starts in one city, visits, halts, and returns. If no one understands, I can explain better. Okay, so you can put this in a graph. You have the cities, every edge is the kilometers. The solution is something like this orange. Okay, so you have the solution. Remember, the MathILS will start with the solution. Then I will explain how do I construct this first solution. So I have this solution. Now I can, this is the mathematical model, I can call a two-up move. A two-up move is remove 2 edges and reconstruct. So I say this solution is a neighbor of this solution. Now you can think about if you can draw, suppose that now I remove this and this. So if I remove these 2, I have to reconstruct the solution. The number of solutions is a polynomial number. So the size of the neighborhood is polynomial. Okay? So this is important. So I construct, so then you can try at home how many neighbors these ones have. In this case, that's 5 times 3 divided by 2 is the number of neighbors. Because if I remove this edge, I can move 1, 2, 3, 4, 5 as the first one. As the second one, I cannot remove these 2 because otherwise I will get the same solution. So I have this 2 only to remove. So if I remove this, I have 2 more, 5 minus 3. And then removing this first and this second is the same as removing this first and this second. This is the number of neighbors. So if I construct all these solutions, I have the neighborhood. Now I'm looking for my best neighbor. And I restart. And I repeat doing this until all the neighbors are worse than my original solution. This is a local optimal. Of course, the local optimal is not guaranteed to be a global optimal. I have no guarantee, could be or not. Okay, so the local optimization algorithm that get the initial solution, it could be a constructive one. So the TSP, I start in the solution, I can be the nearest neighbor. I start on the solution, go to the closest one. Let me give an example here. So I start here, my closest one is here. I start here, my closest one is here. I don't have to wait here. Now my closest one is that one I cannot go because I repeat is this one, this one, this one, and I close this. This is the nearest neighbor heuristic. I construct the solution step by step. When I get the feasible solution, I'm finished. Okay. So you can have, for the TSP, there's lots of heuristics to construct initial solution, lots of them. Okay. But it's a construction. So in any step, I don't have a solution. I finish when I have a solution. It's very simple one. Right? So I construct a solution. Okay, I construct a solution, and then I search for the neighbor. I construct the neighbor and get the best one, and repeat until on the neighbor, the odd ones are worse. So I have my local optimal. Do you get it? Right? There's 2 ways to search here. You can go neighbor by neighbor. As soon as you find better, you immediately restart. First improvement calls, or you can construct the all neighborhoods, and then get the best. Not clear which one is better. The first one usually, in some cases, is better because it's faster. Not clear which one is better. So, so for this algorithm, you see, the only thing we have to do is have an heuristic to construct a very simple procedure, construct a heuristic to construct a solution, any procedure. Like usually, if you talk with the people that are solving it, they use this. Use the constructive solution. If you do course scheduling, that's what you do. There's some rule and you kind of put, and when you're done, you say, don't touch me, don't complain, because I'm not going to change the schedule, because I know I will destroy everything. Exam scheduling the same, right? Or you can do even a random solution. In some cases, random solutions usually are not good, but you can even do a random solution. Then you have to specify what is your move, what is your change, what you're going to change it, right? And then just say, if you're going to do a complete search, look for all neighbor, and then get the best, or just as soon as you get one better, I restart. Okay? So all this is easy to code, and code in 2 days. Okay? Of course, this is the simplest one, the simple metaheuristics. You can see some examples here on this web page. Then I can give you some examples. There's some examples there. So, for example, here, if I do the constructive, I can get this solution. And then how this doesn't work anymore, unfortunately. This is the mathematical model. So we saw it in the morning. So it's very complicated. Why this problem is complicated? Because of this. Because you need to make sure there is no subtours. So this is an exponential number. Even there are other forms to code it much better. But still, it's not so easy. It's a very simple problem to explain, not so simple to solve. Not talking then about the extensions, because TSP is the simplest one, the easiest one you can find in your life description. Description is the simplest one. For reality is much more complicated. Okay, so then for the move, you can have a 2-opt move. Take in 2, put in 2. Okay. You want to try to get all the neighbors here? Let's go and try all the neighbors here. I told you 5 times 3 divided by 2. So let's try it on your paper. So let's do some interactive after lunch. So try to get all the optimal. You can work in groups. So one dance mumbling, let's do it. Okay? All the neighbors of this first solution. Yeah.
It's easy to subtract this way.
Yeah, yeah. You want
It's constant.
it's constant. So do it there. You
in your head.
That is 5 times 3 divided by 2. Times 5 times 2 divided by 2. So that's 5 neighbors. Let's construct a couple. You're going to see that they are not all solutions because the number of solutions is exponential. So if the neighbor is polynomial, is m squared, you don't have all the solutions in the neighborhood. Otherwise, you are in the branch and bound area. That's the trick. Okay? Let's get a couple of them different from mine. So you can see this is the neighbor. This is the neighbors. This is neighbor of this, and then you have 4 neighbors more. Okay. What other moves you have? 3 opt. Remove 3 and put 3 back. It's better. And your neighbor is larger. The neighborhood is larger, so you have to search more. What is balance? Really interesting. Okay, you got a couple?
Sorry,
Yeah.
could you just repeat the question?
Okay, so can I write? No, I cannot write here. Oh, here I can write. Okay, so I have this solution. Let's put another neighbor. This is the 5. Now I maintain this and this. I remove this, and I remove this. How can I construct the solution? This solution is another neighbor of this one. Okay, so we have already 2 neighbors.
So you just keep the same number of paths between.
You keep the same edges, you just remove 2. And there's only one way to reconstruct. If you remove 3, there's more than one way to reconstruct.
Okay, so you remove then reconstruct.
So I remove and reconstruct. So here I remove these 2, the blue ones.
Okay.
And that is I reconstruct. So this solution is a neighbor of the solution. Okay.
So the aim is to ensure that there's 2 edges at each.
Okay, so now another neighbor. Let's see another neighbor. Okay. I maintain this, and this. I remove this, and I remove this. What do I construct? Okay. So we have already 3. So homework, the other 2. Okay. As you see, I cannot. The neighborhood is not all potential solutions because otherwise it's doing full search. Okay.
So there's more than 5 neighbors.
There's from this one, this solution specific, there is 5 neighbors. That's 5. Okay.
So if I were to remove reconstruct, I'd only end up with 5 different neighbors.
Only removing construct, only starting for this one. We call this the current solution. This is my current solution. This is my current. So far, this is my current solution. I construct the 5 neighbors and choose which is better. And then I restart, I repeat. Okay. So I get the initial solution, I get all the neighbors, look what is better and repeat. Repeat until all the neighbors have worst value. Okay. Get it?
If you were reading, how many neighbors did you have?
Oh, if you're moving 3, it's more. It's more. It's much
So it'd
more.
be like
It's n to the 3rd.
So is there like a formula?
formula, because with this one you said 5 times 2 divided by 2. How
Okay, so how many? So let me put the formula here. how many edges we have in a solution? Here 5. So if I have a network with n nodes, I have n nodes. How many edges I have in the solution? Solution, I have n, exactly. Solution, I have n. To choose the first one, I can choose any of the n. The second one, I can, if I choose this one and I choose this one, the solution is the same. But for the second edge, I cannot choose the first one. I cannot choose these ones. So it's n minus 3. Okay, and then choosing this one first and this one second is the same as choose this one first and this is second. So combinatorials is n minus 3 to this divided by 2. So this is OM square. Okay, if we are 3 is n to the third. If we are 4, n to the 4. It's always polynomial, but the size of the neighbor is growing. And we don't like it. Because if the size of the neighborhood is very large, this takes a lot of time. So as some research work, what is the size, the bad size for the neighborhood? That's something in research we do. N to the square works quite well. Then with some differences. Okay?
I see like you use a lot of discrete mathematics.
A lot of discrete mathematics, computer science, everything. Any tool that we can help, we bring it to the, yes. Discrete mathematics, yes.
Like I'm struggling because I skipped discrete mathematics.
Oh, so now you have to go back and study. This, you know, a lot of decisions are discrete, you know?
Could you draw a plot of how n related to optimal solution of a number of, so let's say a number of nodes
So,
is n, and the number of swaps that you do, 2, 3, 4, 5, what that
okay, so
like.
optimal solution, you have to do, you have n factorial numbers of solutions, right?
Yeah. As that increases,
I think
there'll be like a drop-off point, like the plateau, or
here in the TSP, I mean the studies. I've never studied TSP per se because I like a real problem. But the TSP will be something between this. So usually the best neighborhood is what they call the 2-up with double bridges. You know, so especially if you talk with the real, so if you talk with real data, you don't go there and then there and then there and then there. So you can avoid some of the it's a very complex, some of the neighbors you can avoid it immediately. Then I will explain that also too. Okay, so this is the simplest one. Professors, 2 days, they can programming one local optimization. The students can program this in 2 days. A simple problem. Oh, lots of pressure. Okay, so as I said, this is the simplest one. Okay, I explained here. This is the tree move. So you see the tree move, we take 3 and reconstruct. But in the 2 move, there's only one way to reconstruct. No, in the tree, there's more than one way. There is 3 ways to reconstruct. So each removal of edges creates more neighbors. Okay, and so this makes computationally more expensive. What is the comments? So this is a very simple, it looks very nice. There is some drawbacks. It's too simple. It falls down in a local optimal very fast, and not necessarily local optimals are close to global optimals. If you talk about some problems like scheduling, it's proof that is many local optimals which are very, very bad. So it's like my simple example in 2 dimensions here. So you fall here. So if my neighborhood is, everything is inside this round. So here, this is the best solution is this one, but of course the local optimal is here. So we need ways to get out of the local optimal and do it again. Because especially in scheduling, you have, let's say if I could put them in a plane, there's a lot of local optimals, a lot of valleys if you are minimizing. So you can, it go fast, it runs in very few seconds, but the solution is not very good. Okay. So everything else I'm going to talk is getting out of this local optimal. Okay. So one way is to doing multi-start. Multi-start to say, okay, the random solution, local search, random solution, local search, random solution, local search, and then I choose the best. So I can run it anytime. I have 1 hour, I run it for 1 hour. I have 10 minutes, I run it for 10 minutes. Okay, so this I get the initial random solution. Any solution is random. Okay, so I put the courses in the course scheduling as I wanted, and then I wrote local optimal. At the end, I get the optimum. It's good. It's better than local search, of course. It's easy to implement, but usually the random solutions are very bad. So this does not really guarantee you that you come up with a good solution because it's very, very random. Okay, so this grasp, this was invented by the person that invented it was Mauricio Rezende, who was in AT&T, now he works for Amazon. He does these things for Amazon. So he's the one who's really optimizing. Now he's in the middle logistics from the warehouses to the distribution center, but used to be also on the retailing area. Their idea is that, okay, in step two, have a complete random solution at the beginning, you just have like what's called a read and randomize initial solution. I'll explain what it is, and then local search. So it's a local optimal, but this solution is not constructive, but it has some randomness. So the idea is the following one. On the TSP, you are doing the constructive nearest neighbor. So we are in city, we're in Cape Town. So instead to go to the closest city that you have to visit, you choose the 3 closest ones and select one random. So the pure random will be, okay, for all the cities I have to visit, I choose one random. So I can go to Johannesburg and then come out to Durban and then go to, I don't know where, and come back, and this is a really bad. So the idea is a mix between the deterministic constructive and the pure random solution. So you choose for some kind of criteria, you make a candidate list, and then you choose one random from this one, and then you insert the solution. So this is a very simple idea, but you're going to see that I like simple and elegant things, not very complicated. The referees like complicated maths, but I don't. I think if it's useful, it's useful. If it's not, we have to go complicated. So this is a very simple idea. It's something between completely randomness, which could be very bad, and constructive, which only get one solution. So I cannot do multi-start. So the grasp has been a lot of applications, and in reality, there's a lot of applications. I guarantee Amazon has implemented this a lot because they hire him for doing that. It's very simple. It's almost as simple as coding as the other one. You just have to be careful with what criteria you use to select, and then cut one random, some randomness here, which is very simple computationally. Okay. Any questions? So step 2F, so on the construction, you going, so on the construction, let's put this, suppose that this is in a space with this. So your construction, you start here, so the closest one is this one, then the closest one is this one, then the closest one is this one, the closest one is this, and the closest one is this, and this. This is the nearest neighbor heuristic. I construct one solution, step by step. See? The random one, this one, I said, okay, I'm here. From these two are the closest ones, I select one random. So every time I do the multi-start, I'm starting for a different initial solution, but it's not too bad like with a pure random. You follow me? Your face is like, I'm not sure. It's like students. It's like this face like, I don't want to know that. I don't want to show to the professor if I understand it or not understand it. You are doing the same thing.
Isn't that not one of the neighbors?
No, I mean, I'm constructing the solution. The first phase, the first phase. So remember, all algorithms here, you need to construct a solution. Okay? So, I need to construct a solution. That's the first step on local optimization is construct a solution.
So once you've got your first solution,
You do the local, you do
you
the,
do random, when you do a random,
you do the, no, we do the local search as usually, as in the other one.
okay, but
So then you will repeat and repeat and repeat.
but when you start the next one as a random start, your next search space, do not randomly generate a new
Okay, so
off that one with the starting the closest neighbor.
I don't know if I understand. So what I do is that I get the initial solution, the local search. If it's better, I store it and then I repeat. On the grasp, I repeat several times the local search. I repeat several times the local search.
But the greedy randomized adaptive search, is that not taking?
Greedy randomized initial solution is that my first solution, instead to be deterministics calculated, is using this steps that so if I use local optimization, first step, construct initial solution. There's many heuristic solutions for TSP. For example, what I told you. Starting ones here, nearest. This is my first solution. And now I do local search on this one.
Okay, and then when do you get your
This one is different.
randomized initials?
In the first step here. The step to do this, I do some randomness. Let's suppose.
It's totally independent of your initial.
Exactly. So it only changes my first solution. So now here I said, okay, let's suppose my criteria is for the two closest one, I choose one random. So I'm here. These are the two closest one. I choose this one randomly, 50%. On this one, the two closest one are these two.
Oh, okay. So
I choose this one. On this one, the two closest one are these two. I choose this one. From this one, the two closest one are these two. I choose this one. For the two closest ones that are not visit this one, and this one.
you take a random starting node as well.
Yes, so I find the randomness here. The complete random, if I can, the complete random is say, okay, go here, then here, then here, then here, then here, then here, then return. So visually you see that is really bad. The complete random. So choose any one. So this is a mix between the deterministic one goes to the closest one and one choose any one random. So use the set that you can go, which of course it's simple idea and it's obvious. But no one thought about that before Mauricio did it. Okay. So this is a very popular, it's very easy to optimize. Moreover, if you contact Mauricio, he's a great guy. He will answer everything. I think some of the students have even code available. So it's been a lot of applications on the grasp. Okay, so grasp is a good one. And then you can introduce bias. That's what you say on the local search part. You can also introduce randomness on the local search part, not on the first construction, but on the local search part. You can introduce bias, not choosing the best neighbor, but among the best neighbors, choose the one random. That's what it is. So you can choose random. Why randomness introduces helps? Because then you can repeat the algorithm several times. And every time you have a high probability to get different solutions, different local optimals. That's what you want. Okay. Another way to get out of the local optimals is the work by Fred Glover. So the Fred Glover work is a different strategy. What they did, remember, we always try to get more solutions besides the first local optimal that we get. What Fred Glover did is say, okay, I do the local search, but I try to avoid repeating, to undo things that I've done in the past. So I put some things that are taboo. So if I remove two edges, I will avoid these two edges cannot put back on the next number of steps. So I forbid them to, when I remove two, I'm not talking about the local search part. I remove two edges, I cannot put back these two edges again. Okay, so these are taboo. It's a taboo list. Okay, so this is a little bit the idea, and then they have a lot of things that it does to improve the search. For example, if you think about the TSP, okay, if you have a very large edge, you know that probably that very large edge will not be an optimal solution. So you can say this edge will never go back for several iterations. I will not use it. So I intensify my search on the good edges, which are the shortest ones. Okay, so this is strategy to intensify. Or if you get an area that is better, you really search on that area. For example, try to remove the largest edge first, because there's a smaller probability this large edge will be. So you have this intensification and diversification strategies that Fred Glover discovered, that to say, okay, if you have a good solution, search more on this. Or if you are repeating, your local optimum is always the same, so stop that and introduce a very large has to change the solution. So these are strategies that the Fred Glover is described. I'm not going on the taboo search, which is a little bit sophisticated. But the basic one is that, okay, you see, get initial solution, always get initial solution. Then instead of the local search, we have a similar local search, but we only consider moves that are not taboo. And when you perform the move, that move becomes taboo for a certain number of iterations. So the TSP is that if you remove two edges, these edges are taboo. They cannot put back on the next several iterations to avoid going back to the same. An advantage of this is that you can run this at the time that you need it. You need 10, if you have 10 seconds, you run 10 seconds. If you have 10 minutes, you run 10 minutes. At the end, you get the best. Taboo has done very good results. Very, very good results too. It's one of that is really good too. So designing a taboo search is simple. You need an initial solution. You always need an initial solution in this algorithms, always. Could be a constructor or random. You need to find a neighborhood. You need to define if you do a complete search of first search. It's the same as the other ones. Now you need to define what is your taboo criteria, what is define the expression criteria, the identification, if you have them, and then the running time, how much time you want to run this. And these are problem specific. Okay. So here the taboo is the idea that the Fred Glover uses this paper uses a two move. Taboo list consists of the shortest edges of two deleted by the move. So we will remove two. The shortest edge, it's taboo. You cannot put it back for a certain number of iterations. Okay, it's in the taboo list. It has a duration of iterations, this one, because then maybe you want to put it back. Okay. And then another one uses the pair. It puts the pair on the taboo list. So this depends on the problem. Okay. Oops, I did something. Yeah, I just put the wrong button. It produced very, very good results in very, very small times. And that is a lot of, it's much more sophisticated, much more complicated to implement this one than the local search. And this you need to work more on the problem. Okay, so this one is the one I will present next in detail. Just again, the idea here is a little bit different. Remember, we always want to get more solutions at the local optimal solution that we get with the local search method. The idea is very simple, is that, okay, what we do the local optimization, heuristic, initial solution, local optimization, then you do a perturbation step. A perturbation step is that, okay, you have a solution coming out of the local search, and I change it. I change it, I make like a big change, and then I repeat. The local search, make a big change, and I'll repeat. Make a big change, and I'll repeat. For example, in the TSP, I will explain this in more details. Could be, I do a 2-opt on the local search, so I do a 2-opt. On the perturbation, I do one move of a 4-opt. Remove 4 and put 4 randomly. 1. Then I repeat. Okay. And since I only do one move here, This is computational less expensive. Right? And then there is, again, local optimization, and I repeat this until I'm happy. Okay, but I will go back to this one. And then there's another set of algorithms. So right now, the metaheuristic that I'm explaining are, I have one solution, change it, one solution. I always work with one solution all the time. I have one solution. So the genetic algorithms is that I have a population of solution, I change this population and create population, then I get happy. Okay? So this is more like a population-based algorithms. It were created by computer scientists, which was very good. The problem is that with the let's say traditional genetic algorithms in combinatorials does not work. Okay, so we need to do some more things, because if you want, for example, do crossover in the TSP, you can do crossover in TSP or say, okay, I have two solutions. I get some edges from this solution, some other solution, then create a new one. That is not a feasible solution. Okay? Let me give an example here. So the crossover is like the crossover like in genetics. So suppose I have these two solutions. The solutions, okay? I'm going to create the child, the next generation. I pick this one, and this one from this one, and I pick this one and this one from this one. So this is not a feasible solution. Okay, yes.
Not to be pedantic, but what is the chromosome representation in this example that you are creating?
It's complicated also.
It's
So that's why in combinatorials, I'm going to show you another genetic algorithm that works much better than this one, in my opinion. Because it's very complicated, the chromosome representation. It's not easy to represent it.
So they normally use like edge recombination operators, and there's a couple of different ways of sampling edges to make sure that you guarantee that you get two.
Yes, but then you need to, yeah, so usually the idea is that, okay, I have to do more things than the simple genetic algorithm. I have to do some kind of heuristic to make sure that this is feasible.
You're making it sound like mathematical programming was easier. We should have just gone that way. It's so hard now.
Now, this is hard in genetic algorithm. So in combinatorials, you don't see many genetic algorithms work well unless the things is, you know. I can give you an example. When I went to Barcelona, I went to work to a company, consulting company that was doing the timetabling for the Olympic Games. The 92. So they have done the 92 Olympic Games. They come out everywhere to use genetic algorithms. I arrived later, and I said, you know, the advanced scheduling for the Olympic Games, it's not an easy one. It's a lot of constraints, because just give you two constraints. The swimming pool has a lot of events. Right? There's different events of swimming, the water polo. Okay, so this is one resource. There's one resource for many events. It's a scheduling problem, and moreover, you cannot schedule the final before the semifinals. And between the semifinals and the final, there is some time. You can jump to the semifinal and final of the same event. So they said they come out and use that they use a genetic algorithm. That I was like, it does not ring a bell to me. I mean, how do you do it? I mean, this must be amazing. There's something that, and I keep insisting to the person that done. What he did, it was a constructive, pure, simple heuristic with some kind of rules, some kind of what is common sense rules. But they, of course, they sell it as a genetic algorithm. But it was never a genetic algorithm, because they could not perform this, because there's a lot of constraints. So highly constrained problems, the more simple genetic algorithms does not work. There is some work published on very sophisticated genetic algorithms, and then I agree with you, much better do branch and bound. I mean, if you do such a sophisticated, it takes a lot of time. So remember, it's tools. So if you have a branch and bound, you can do, it's much better. Okay. So this is some of the issues in the pure genetic algorithm. So this is just to give you an idea. That's the idea is always get a population of, could be random solutions, and then create population by using the select the best elements, crossover or mutation, and then at the end you choose the best fitness. That's the word. Another genetic algorithm that do work on combinatorial optimization is also proposed by Mauricio Rezende. It's what we call biased random key genetic algorithm. And this works very well when your solution can be represented by a stream of numbers. The idea is quite simple, is that your representation of the solution is a stream with real numbers. And when you sort them, you get your solution. Okay? For example, when you sort this one, your sequence is 42135. So for the TSP works. For the TSP works. So you do the genetic algorithm, all the crossover, mutation, everything on these streams, and then you just need to have some kind of algorithm that transforms the streams on the solution. Okay. So this is what you call the bias random key, was proposed by Bean, the random keys, but the bias was proposed by Mauricio and other person, I don't remember the name. The idea is the following, okay, it's the same. The best solutions go to the next generation, so they survive, and then you do crossover, and then you do mutant, so this is the next generation. But the idea is working all the way with the streams. And with the streams, it's easy to do crossover. So we have these parents, you select random which of them, you create this cell, which is a representation of the solution, then you can get the algorithm to transform this representation on the solution to your problem. Okay, Gonçalves and Rezende, that's the paper. And the nicest thing to implement that this is implemented. You just need to implement the decoding for your problem. So all of these are already works with the streams of real numbers. You just have to understand the decoding. Okay, so understand the decoding. I don't know. So the decoding is the only thing that you have coded. In reality, I think even Mauricio has all this already available online. At least one of your PhD students, I think he coded it, is available online. Okay, so the decoded is only thing. I don't have, we did an example here with this heuristic for collecting blood samples. Collecting blood samples from, I don't know here, but in Barcelona, so if you need a blood test, you go to a place where there is only one room and they collect your blood. This blood has to be sent to a laboratory which is outside the city. So they have many collection points in the city, but then they have to collect this and send it outside. This problem is like a vehicle routing, but with a lot of complications. First, just to give you some ideas, is that the route must be smaller than 2 hours. Because if they shake too much the blood, then it does not arrive in good condition. Must be a cold transportation, so we need to have cold. And like here, summer could be very hot in Barcelona. Must be not, they cannot go on mountains, because if they go on mountain streets, it shakes too much the blood. So there's a lot of constraints. And what we did is exactly using this one isn't the decoder. The decoder was very simple. It's just you sort like here, we sorted and then say, okay, if the truck only have two boxes, we have 2 in one truck, 3 in another truck, and 5 in another truck. So the decoder is very, very simple because there's a lot of constraints. So we can all the constraints go on the decoder. We don't have to care about all the rest. So this bias random key, for me, genetic algorithm is pretty good. Is one of my favorites among the genetic algorithms. Okay, and then I'm almost finished. Yes. So then we have hybrid metaheuristics. This is a name done by Christian Bloom. Is working a lot on this. These people, special Christian, is okay. So we have taboo search, we have local search, we have graph, we have bias genetic algorithm. What a mess. So, but then we can put everything together. We can use these are like a Lego pieces. you can construct your algorithm with the pieces better for you. So it's called hybrid metaheuristic. Okay. And finally, there is also what we call MathILS. This is also new. This is a group of Italians that are in Belgium, which are very good at marketing. MathILS is why not mixing integer programming exact methods with local search? Why not mixing them? Because some things you can use exact methods. Suppose you have a TSP with time windows. Okay, you have a fantastic algorithm for the TSP. You can run it for that and then check if your time windows in some way, time windows are included in the metaheuristics. So the idea here is to exploit incorporating exact methods in metaheuristics or incorporating metaheuristics in exact methods. For example, have a simple metaheuristic to get the initial solution and then run the branch and bound. So you already start with a good solution. So your branch and bound can go faster, or vice versa. Okay, this is exploiting various ways to exploit the incorporation of exact methods inside the metaheuristics or vice versa. This is what we call like a little bit, and have been some work done in this. In reality, I did after my PhD thesis, I did one of the first of these metaheuristics. I was not good enough to call them metaheuristics, so I'm not a very good marketing. And the idea was to, we have a very complex scheduling problem on the perturbation phase. I will explain this later. I use an exact method. I use an exact method with a problem that is smaller. So some problems, if are smaller, I can solve it very well in the exact method. When they're bigger, they might have problems. So why not solve it? So I really optimize one part of the problem, are very good, and then with the local search, I reconstruct the rest. So that's a little bit what I've done. There's some people that have done, this is very interesting, is instead to have the crossover to be random, you solve an exact problem. So you get several parents. So for the set covering, well, I don't want to go on set covering. You have several parents, and then you optimize and get what we call the perfect child. The child was perfect for their parents. Not the optimal, but it was perfect. So this is ideas to mix them of them. There's some other work done also for trying to reduce the neighborhood and look for the neighborhood in a more efficient way. So there's several work done in this area. And here I give you some examples. For example, if you have a vehicle routing problem, each truck is a TSP. So you can solve that as a TSP. TSP is well, it's difficult, but there's very good algorithms now. You can solve it very fast. Okay, of course, this is not guarantee that the solution for the VRP is optimal. So you can have moves changing one customer to one route to another one, but each route will be the best possible. Or using dynamic programming here, there's work done by Ibaraki in Japan, or using some dynamic programming to use a large neighborhood, but to reduce the search. So there's real interesting work here. So my next talk, after the talk, I will explain exactly the iterated local search, but I'm glad I did the metaheuristics because I realized you didn't know metaheuristics. So we go directly in the iterated local search, you will get lost. So I will explain the metaheuristic extensions of the iterated local search, extension of the iterated local search, and a real example. Just kicking me off. You talked too much. Okay, and I will give you some examples of this. But as I said, for very large scale problems that you need to solve far, maybe in the future with quantum computers, this will all disappear. We need some other tools. Yes.
So what you're just talking about with heuristics is using metaheuristics first and then exact solutions, or is that applying exact solutions, deriving exact solutions, and then applying metaheuristics?
Let's see, depends. So okay. If you're doing research, what we do is we don't model the problem, a mathematical problem, solve it with Gurobi, Simplex, whatever your favorite exact solution. for small instance. And then we tested, compare the metaheuristics with the solutions from the exact methods, and we tested with the largest one. You're going to see some examples here. If you go to real life, I mean, maybe I record this, right? If you go to real life, they wanted the best solution that you can give them that is profitable for them. And usually they give you a very short time. So we go directly to ML. Unless, I mean, there's some companies that are willing to invest, but it's an investment. And I always offer the companies both options, but the other one is an investment.
In the previous talk, because as far as I understood, the previous talk was looking at an exact solution, and they got stuck at a non-optimal solution on an exact model. If you switch that over to a metaheuristic step, just to randomize it a bit and then continue with the
trade-off is in an exact model. So when you're watching the Groby solve, you notice he was talking a lot about the lower bound and the incumbent. So the incumbent genetic algorithm was produce an incumbent, but you have no reference point for how good it is. Whereas the exact methods will tell you, okay, actually, we know that the solution cannot possibly be better than this, and your current solution is up here. It constantly monitors the gap, and the moment that gap gets to zero, that's when the proof is complete.
Yeah.
So genetic, all the meta-heuristic things kind of fly blind in that they don't know how good they are, but they do it really quickly.
But
so maybe that's okay.
But what was happening? What happening with that is it was getting stuck at a point here. I don't know what the innards of the algorithm was.
If it gets stuck, yes, we do graphics. If it gets stuck, our search gets stuck, we can stop. You can stop the metaheuristic there, or you can restart with something else.
Well, wasn't that an exact solution? Finally, so throwing a metaheuristic to randomize it a bit and then continue, or would that not be feasible?
It's tricky in that context. The exact solves in that space there. What actually happens is your objective claim is getting no information about how to search. So it's eliminating parts of the search tree as it's going, but it's not really typing the bound, which is why as soon as you tweak the problem, they type the bound. So they're kind of different, but you can mix and match whatever. The metaheuristic is nice. It's like put the two together. If one's working well and you've got a sub problem that's always solvable, then use it.
I can understand why you would do metaheuristics first and then look for the exact solution. I'm just wondering about the viability of looking for an exact solution, then applying a metaheuristic. Computationally.
If the problem is too big, you cannot do an optimal solution in reality, or you need a lot of time to invest. I'm going to give you an example. We did a project for a company called Cabify, which is like a Uber style. Okay, Cabify has to assign drivers, and it runs this algorithm every hour. It needs 30 seconds to get solutions. Right? They come to me because they have this mathematical model, and they come to our group. In reality, it was Jessica who did this. Come to mathematical model. This is taking too much time. It's taking half an hour to get the solution, but we have to answer this in 30 seconds. What can we do? So the first thing we did was we changed the formulation. So they have a direct formulation, and we formulated as a set covering, which runs very much faster. Even that will take 20 minutes, 15 minutes in some cases. So said we have 30 seconds. What can we do? Okay, so they have to answer. So the band arrives and they have to answer in 30 seconds. So so far, and as I said, be careful with the message, because I don't want to be this exclusive person that's how we have to do metaheuristic, or to do exactly. There are tools. So we have to choose the tool that is right. And then the company can say, okay, we can investigate this problem and try to get another formulation, cut this, but that costs that. You are paying the researcher, paying one researcher and 3 students. That's the cost. They say, we don't want to pay that cost. And we should not charge low. One professor in marketing say, if you charge small amount, you have small value.
If you don't drive a Ferrari to a job, then they don't value you.
So sometimes I try, which never no company accepted me, is I will charge a 10% of the benefits. One of the company we in our test with he never bought the algorithm. He reduced 3,000 euros a day. So 10% in 5 years, I will retire. So, but this is something it's important. I mean, the value of research, the research of all of this as a value, as a high value. You study for many years. So in this case, the company didn't want to buy that. So I could research on the good formulation, which is fair. I mean, the company makes that. I'm not saying, and I mean, the company makes that calculations, and we have to think the company has to. Any company has to have benefits, so they make their calculations. So it's important to see that for some cases, it does have a cost to go on a MathILS thing that we can have a cost. And then let me just finish. If you go to the social work or healthcare, most of the organization we work at NGOs. I'm going to charge NGOs a license of growing. I'm sorry, but they will not pay it. They all want open source. That's all they want. So a company says, by policy, we cannot buy any license because we are receiving donations and we have to justify to people that donate the money where we spend that money. So remember, it's a tool. If you get the optimal solution, then some cases, even it's the optimal solution with this stochastic data, I have my questions, my research questions. But if you get the optimal solution, you can solve it, fantastic. You don't need any of this. And these algorithms are becoming much better lately, much more efficient. They are improved significantly. Simplex, any of this. Computationally becoming much better. Okay? But it has not a unique answer, in my opinion. It's not like, okay, this is the best. But like life, right? Okay, so finish this part. So now we can talk about SimILS. This is another big name, which means simulation and heuristics, especially when you have stochastic things. So we'll talk about some examples that we've done here. What is the optimal solution if you have stochastic data? I want to go to the airport on Wednesday. The fastest route. What does it mean, the fastest route?
Just expected route.
The fastest expected route. And is the fastest expected route enough or the more consistent one?
On average.
On average? But if you have like some kind of product that you need to maintain and
now we're talking multiple objective stochastic optimization.
Is the average enough or do you have like 80% or I'm just creating questions?
No, I get the point.
You get the point? So it's the average is good, but is it the average good? Is it the average good for you? If in average every time you take the bus goes on average on time to your or do you? I always tell this example to take my kids. We don't go to the school anymore, but they used to go. They have two routes. One is the shortest one in this, but I can take from half an hour to 2 hours. That's the observation. And another one, I will always take 45 minutes every day. Which one do you think I choose? Oh, right? Okay, so this is an interesting question. So we have a solution for try to solve this question a little bit. So to put a small here, so which I will talk this later. And then there's this one. I'm not going to explain this because this is the work of my colleague, Jessica de Armas. If you want to ask her, she's the expert. I have no idea. So I trust my team. And if I have an expert in my team, I don't need to be the expert on the team. So that's why I'm the director, right? So I try to have experts in many areas. So Jessica is the person, this person here. She's an expert to mix machine learning with metaheuristics, try to understand the behavior of the solutions and then construct neighborhoods that perform well. And so I'm not going to explain anything. So she's an expert. I think this is a very interesting area. Very for research, this is a hot topic in the next years. Okay, local search. There's only one commercial software, as far as I know, which is this French company. If you are an academic, I think you can have a free license. At least I have a free license. It's very tricky to use. You need to have a computer engineer to understand it. Not very user-friendly, but you can do it. So this is a French company. Here, how it looks like. So you can model the problem in a way that you do in all this Simplex, Gurobi, whatever, MPL, whatever software. And then we got the question, which is the best metaheuristic. So I'm showing a little bit, and now I'm going to say that for me is Iterated Local Search because I, in a way, work with this one, but you can choose anyone. Okay. So coffee time break, and I talk too much. All right. Thank you. 50 minutes, is that okay? And if we finish early, we go early to work. 15 minutes, is that okay?
How do you get around the belief cycle time, right? So there's getting to the right answer based on the math, and here's the answer, but then there's the problem of having the answer believed, right? Often when you're dealing with opinions or really experienced people say, I know what we're doing. Just any thoughts on that?
At the end, I have a PowerPoint lessons learned, and I can give you just one hint. We start like you don't know anything about business. You're a university professor. You cannot teach us anything.
Yes.
Lot of barriers, lots of issues. They call you for everything, every problem. That's not an optimization problem. I'm very stubborn. I will, and I learned by making a lot of mistakes how to talk with business. But it took me a long time. So I'm old already. But it's usually come from, and then I will give you one specific case where it was like, they receive it because the boss said we have to receive it. But since you enter, it was like a stone on the way, always, until now they call for things that say, no, this is not an optimization problem. I don't have no idea about human resources or marketing plans, or, I'm sorry, but I know how to solve this. I'm very limited. So it goes usually, but I will tell some stories. So let me go to some stories. So let's jump this because I read this. So this is some companies that we did consulting. I will explain a little bit of this. So iterated local search is a local optimization metaheuristic. So we have to start with the initial solution, but do local search, but then we repeat and repeat this until we are satisfied. The difference from the local optimization simple method, which is this part, is this perturbation step. This is the really difference that's simplifies. Remember, I want something simple, fast to implement, and can get good results. So we don't want very sophisticated algorithms. So this is the perturbation, and then we do local optimization again, and we repeat. So this is the simple implementation is very simple to do it. You do a greedy metaheuristic, like a constructive heuristic to construct the solution. You do the local search method, and then you have to define this perturbation. It could be what I call a high-level neighborhood. For example, for the TSP, I can do 2 moves here, and I can do here 1 move of 4 opt. Put 3, 4, and put 4 back. Just 1 is fast. So this is very fast to implement. And it requires very few lines of code, and it gives very good results. If you want to go 1 step further, do more better, then you can do, on the local search, you can do something like taboo search, like a better, more sophisticated local search method. And here you can have a lot range of perturbation, even doing what we call optimized perturbation, which is solving optimally a smaller problem or a simple problem, okay? And using other types of heuristics, okay? the important things in iterated local search is this relationship between local search and perturbation. I told you about TSP 2-opt, 4-opt. In reality, this is not very good because the 2-opt and 4-opt are similar. So it's interesting thing is that the perturbation is very different from the local search. The idea is that imagine that you have the space of the solutions. Yes, you have the, so this is the space of the solutions. You do local search here, and then the perturbation takes you to another part of the space of the solution. Really change the structure of the solution. The structure of the solution is changed. Then the local search will optimize the objective function, but the structure of the solution is changed completely. Even could destroy the solution a lot. Okay, for example, TSP, you can say, okay, I take 4 edges and put the largest one. My solution is really bad. But then the local search will improve it, but the structure of the solution changes completely. So in the perturbation, we have to look for the structure of the solution. That's really things that destruction, construction things, or solving optimization problems. So this is really, the idea is this relationship between local search and perturbation is interesting because you need to change the type of solutions you have on the perturbation. You're not getting a good solution necessarily because then the local search will improve that solution. That's the really things. It's becoming very popular. I get this from the Google Scholar. The entries is not the citation, are the entries. So it's a little bit different. So it's improving, but it's interesting is that more and more people are using. In reality, the iterated local search is nice because it has all the advantages. Remember the 4 advantages of the metaheuristics. It's very simple. Very simple. It's not, you don't need any. It's very flexible because you can change the. So if a solution is not feasible, you just ignore it and go to the next one. It's very fast because it's easy to implement and it gets very good results. All the studies in some problems is the best metaheuristic that exists. I like to give this also a story, especially for young students and PhD students, how do we arrive to things? Sometimes it's a coincidence. So I was doing my PhD at Cornell and my advisor said to me, look at this working paper. It was a working paper. This working paper was done by Olivier Martin on his PhD, he's a French colleague. And I thought the idea was really good. It's called large step Markov chain of traveling salesman problem. The other day I threw away all the papers I have because I don't need them in paper anymore, but I keep some of them. One of them is this one. So I thought the idea was really, really interesting. So this was based in Lynn-Carnegie local search heuristics, and it gets very good results. There it was for the TSP. The local search was a 3-opt, so taking 3 and putting 3 for the TSP. And the perturbation kick move was a random 4-change move on a double breach. So it was a specific change on this. So I thought this was brilliant. So I applied to my PhD thesis for scheduling problem. I applied to my thesis in scheduling problem. In reality, it's a shop scheduling. So for those of you remember, it's a scheduling. This is a priority dispatching rule. Local search was a 2-opt. I used also a simulating annealing. And the perturbation is really interesting. So a job scheduling, for those who don't know, you have a set of machines, and you have to schedule a job that goes in different routes for each machine. Okay. So what I did, so this is NP hard, it's a difficult problem to solve. But if you get one machine scheduling problem is easy. You can solve it in polynomial time. So what I did is say, okay, forget about all the machines, optimize only one machine. That machine was perfect. So I solved to optimality one machine scheduling problem. That machine is perfect, the other ones were really bad, and then the local search will fix the other ones. Okay, so that's the idea that I got from this paper. Okay, then later on I did something more on applying this to local search, simulating annealing. I did some other work. Okay, in reality, it was one of the first hybrid metaheuristics and one of the first metaheuristic. But as I said, I'm not very good on branding. Then I knew that Thomas Schutzler also got the same working paper that I have, and he really liked the idea too, and he applied it on there's a technical report for the perturbation flow scheduling problem. So we did this. We met, and the first met on the first one. It was the second MathILS conference in Brazil. So I met physically Tom, and I said, "Oh, I use this one. I used. Oh, it's great. Let's know." And I said, "Why we don't do a paper like explaining the MathILS?" "Oh, but Olivier should be, because Olivier was like the father of all this." Okay, so we did. So we did this famous paper with Olivier Martin. I've never met Olivier Martin personally. I changed a lot of mails with him. One time he come to Barcelona, I was away. So I've never met him personally. With Thomas, yes, I met him. He speaks Spanish. It's very interesting. But with Olivier, see, we never met personally. So distance is not a problem anymore. This is all the names he gets. And finally, it was Thomas who decided to call it Iterated Local Search. It was the one who branded, but we call it the large step Markov chains was what with Olivier Martin comes. And there's many applications. It's very interesting. And as I said, for the TSP, so for the example is to have a two opt here, a 3 opt on the local search, and only one move on 4 opt double breach system. Okay, so the double breach is when you have things like this, you undo it. And we have things that crosses, you undo it this. So that's the idea here. Let me give you now examples. So this is the first example on the click. Remember, I told you about the click problem. We wanted the maximum cut click. So we want to find a click. A click, remember, is a set of nodes that are all connected among themselves. So this 4 is a click. You see, are all connected. But we want the click that has more connections on the border, a cut. And I'll give you an example of that. So we did this. So the local search is very simple. We add nodes, we remove nodes, and we change nodes. So for example, here we have a click. I can put this inside and calculate it. Or then if I have this click, I can take one out. So add nodes, remove nodes, so I change nodes. So that's a very simple move. This is the local search. The perturbation is more complicated. It's like we select a node, we put it in the click, and then adjust everything to make sure that is a click. But we only do one move, remember. Perturbation is just one shot. Okay, so that's what we did. Look at the results here. So we run it with SimILS. It was a couple of years ago. We give 1 hour to the SimILS. So the time is in seconds. For the shortest one, so this is the number of nodes, the number of edges, okay, of the network. So for the smallest ones, we always get the optimal one, always. This is the SimILS. So we get the optimal nodes from the maximum click and maximum cut click. For this one, from the maximum cut click here, we could not solve it. Could not solve it. After 1 hour, the computer didn't have any solution. Not feasible solution, nothing. Okay, and when we do the iterated local search, you see we get always the optimal solution for the cut click. Always the optimal solution. We get it for in a very few seconds. You see the seconds? Very fast. Why do we want to solve this problem? What is the application? The application is what's called market basket analysis. A market basket is when you go to the supermarket, what you put in the basket. Okay. So let's go back to the analytics. So the companies now, most of the companies in Spain, some years ago was worried about, they have this fidelity card to give you offers. They don't do anything with your data, just giving offers. Now they're doing some analysis and some forecasting, but here we're going one step further. So everything goes on the basket. And this is very important information because you can relate products, you can see where to locate it in the warehouse. So there's a lot of marketing things. And this can be represented in a network. Each of the nodes is a product, and there is one link if a certain number of people put it together. I go for beers and chips, And a lot of people buy beer and chips. Okay, so they can construct this network. Usually there is a threshold, so there is an edge if there is a certain amount. You can even put a weight, but the company tells you only after this threshold makes sense. So what we wanted to look here is for the click. The click means the products that have more influence in the other products. So other products that are related to each other and they can influence more the other products. Okay, then you can offer, so if someone buys all these products in the click and the other ones on the round, you can offer them the other problem. So if you do the maximum click, which is a lot of marketing can do in the maximum click. So this is the maximum click. Okay, this is all the products that are related among each other, but they have very little influences on the pie. If you do the maximum click, so doing a marketing campaign on these ones, you can get all this to be impacted much more. Okay, and this is a little bit what we did. Oh, I don't have the pictures. It was, in this case, it was we applied for ice creams, and the company, what it did is that it did a campaign on these ice creams, and the sales incremented significantly. Because this person that buys all this person will buy those, so you can relate to them. Okay, this is something that we did with the database from UK. This is another example. It's not mine, but I think I'd like to because I think there's a plenary about water distribution, and this is another application. Iterated Local Search is very interesting, which is the aim is to find the best diameter for every pipeline in a network. Okay, we have the reference here. I'm not going in detail, but the idea is to have, okay, so generate initial solution. Okay, set the largest available diameter, set commercial available in pipelines type, this one. And this one was a move that tried to decrease this, and the perturbation was just a random. Look at this, this is interesting. Just a random move here will help to increase the best solution. That's a little bit, just go a little bit. So the algorithm really gets really nice results on some of the benchmarks on the literature. Oh, this is the reference. So this is the reference that I give it to you mostly. This is the last one. And you see as myself, Martin and Thomas, Olivier and Thomas, and I never met Martin, which I said I should. What extensions now? What are we working now, which is very interesting? Of course, we can hybrid with other metaheuristic when do bias, simulation, math, and two-stage. So this is the ones I wasn't going to explain. These are the ones that I'm applying more. Okay, so special because the problems, we'll try to look at uncertainty. This is very important, look at uncertainty, and also to get really good implementations, a little bit more sophisticated than the very simple ones. Even the very simple ones work. Okay, so you can hybrid. So instead to use local search, you can use Taboo. If your local, for example, is scheduling. I told you already, scheduling has a lot of local optimals. It's a lot of, you run it 2 seconds, then you already have a local optimal, which is really bad because it's, if you look at it, it's like a lot of alls. So it's a local search is really not good. So we have to have a better algorithm on the local search phase. So we use a Taboo or a variable neighborhood search. The perturbation, you can use a very large neighborhood. So this is like one step further, more sophisticated. Let me give an example. This is a company in Spain. They produce basically meat. Okay, this is a company that controls all the supply chain. They grow the animals, they kill the animals, they cut the animals. I'm sorry, and they put them in a basket and take it to the stores, and they have their own stores. So they have the full supply chain. In reality, it's a company. Usually, food companies are very local. So, but this is a company that all other business are looking what they're doing because they've been very innovative in many things. They used to have, they still have like a CEO, which is very original. He creates really improved in all kinds of businesses. So this company has a warehouse. It has to distribute for about 500 stores in Spain, mostly in Catalonia. So there are very few in Madrid and Valencia, but mostly as so they distribute daily, every day. They the business strategy for them is that they have only 3 sizes of products. So the what to say the trays they come the food the meat are only 3 sizes, and they're very basic meats. Full chicken, the legs and wings, and it's so if you want something meat sophisticated, you don't go to these stores because it's very basic. But since the price is very low, it's very popular. If you go at the afternoon, like a Saturday afternoon to this store, they are completely empty, basically. And you know the product is very fresh. So this is a very original company. So they have to distribute every day. They have 7 different trucks, type of trucks. They have a very specific time windows to enter. They have all kinds of constraints because some of these stores are in the center of the city, which is only small trucks can go, big trucks cannot go. And they have even limitation to enter, the time they have to enter, where they have to park, all kinds of constraints. They have, of course, massive driving hours. They have multi-trips for some vehicles because some vehicles can do a trip in the morning and a trip in the afternoon because the stores are located close. And they have, of course, sales constraints. And we want to minimize the operative costs. So we knew the costs of the company. Okay, so we did this with some people from Brazil. And the structure of the iterated local searches, the initial solution was a grasp, because we need a very good solution at the beginning. So we did a metaheuristic in the beginning. And then the local improvement was a variable neighborhood descendant, which is another metaheuristic that I didn't explain, which is you have different neighborhoods. Instead to have only one, you have different neighborhoods. These neighborhoods are like descended in the size, but basically. And then we have here a more sophisticated random neighborhood, which is was very sophisticated. So that's what we did here. The paper is published if you want to look at the details. I don't want to go into the details. I want to go more on the application. This is the study that we have with some data. I cannot show you more. Of course, when we work, especially with businesses, it's very difficult to get them to show more results. But I can show you this. This is comparisons between them and the best and the average, and the company. The best is the best solution we get. The average is the average solution after so many runs. And you see, we reduced 10% on the costs. Okay? This is a lot of money. This is quite a lot of money. Okay, this is quite a lot of money. Unfortunately, the next director didn't want to implement it. The first director did, and the second director decided to buy a commercial software because the maps were nicer. And he asked us to do the maps. I said, no, the maps is not research. I mean, I can, you know, that you can hire some professional companies. I mean, I can hire that. I'm not going to do the maps. And I mean, I have to hire people, and my people don't know how to do the maps. But now I think the following director did use it because they bought the software. Okay, so this is a little bit. This is very interesting because this company is quite. Business schools really look what they are doing, even it's not no international. Okay, so we save about 10%, and then another story. We won't try to publish the paper. What did the referee said? They said, oh, you have to compare with some benchmarks. There are no benchmarks in this problem. The problem is so complex that there is no benchmark. So we simplify the heuristic and compare with the closest benchmark that we could find, which is an algorithm by Prims, and we produced 2% better than Prims, and they were happy. Useless, in my opinion, research. Because it won't go anywhere. I mean, but they wanted, we need to publish. We did it, okay? And that, not only we reduced the cost, we could improve the coordination with the sales department. So the sales department could have in advance what the routes are for distribution and could change in a way the truck, because since the stores are owned by the company, they can put more product. So they could see what trucks were not full, and they could analyze if they were worth to put more product in that truck related to with the sales of that stores. So that's one of them. Another one, this is This is something I cannot talk much. So all I will tell you is I'm allowed to tell you, but not much. This was for Zara. You know Zara? There's a store here. I saw it yesterday. So Inditex, in my opinion, is one of the companies that are really doing smart businesses. They're really smart. They're doing really amazing things in terms of management. And they ask us to help them to schedule the picking of the orders this is a Zara store, a Zara warehouse for online. So Inditex, I don't know if you know, for the store, they have only 2 warehouses in the world. So there's one warehouse in Arteixo, one warehouse in Zaragoza. And from these 2 warehouses, they provide every store, including South Africa, twice a week. So every twice a week. So the secret of Inditex is that they analyze everything. So if you go to the Inditex store, to Zara store, you will see it. I don't know here, but I've seen them many times in Spain. You see the manager of the store looking at you. And they say, and this is well known. So for example, you know these jeans that are cut? So this comes in Japan. They realize the Japanese are literally changing the fashion, and they realize the young people cut the jeans this many years ago. So they say, why won't you sell it already cut it? Why do you buy a cut jeans? That's what my grandmother will say, right? Grandmother say. Okay. So the Inditex say, okay, if they cut the jeans after they buy it, we sell them already cut it. We has it all over the world. Okay. So they have only 2 warehouses, but for online, this is not possible. The supply chain is not possible to deliver in 24 hours or 48 hours if you don't have a local warehouse. So they need to create local warehouses for picking. And in this one, it's in Madrid, they prepare on average 30,000 orders a day. And in Black Friday, I don't know if you have Black Friday, this American thing goes all over the world. So Black Friday is 500,000. We have 24 hours to prepare 500,000 orders. Okay. So we went there, and there was a consulting company from Madrid that they were running the software on the warehouse, and they asked them to do the algorithm. They didn't know it. They come to us to help them, and we prepare. So we look for the problems. I went to the warehouse. I was in the morning during 1 hour picking the orders. I was very bad, I can tell you. with the logistics director of Inditex, we were preparing orders so I can understand the problem. So one lesson, I did it myself. Okay, so I couldn't understand what was the problem, and a lot of input data. So the idea is that the orders are coming. And every half an hour, they have to run the algorithm for 1 minute, 2 minutes. The orders have to be prepared on time to go to the truck. So there is a schedule of the trucks, which is also optimized. So for example, if the orders for Barcelona are prepared in this warehouse, the cutting time is 10 o'clock in the morning. So the orders have to be prepared at 10 o'clock in the morning. So depending on the orders, there's, I don't know, thousands of products in the warehouse. So the same you see in the store. So you go to the Zara store, here, start counting. See how many times I send my students to do that. Because think about a t-shirt has a color and size. Model, color and size, multiply by 3. Okay, so you can imagine online, they have even more things. Okay, so millions of SKUs. And then you have to say what orders are going to be prepared in the next half an hour. Associate each order to a person to pick them, and route that person. Okay. What they do, they don't prepare one order and another order. What they do is myself and Georgina, we both ask for a white t-shirt. They go and pick 2 white t-shirts. And then they have a table, and then they spread Georgina order, Helena's order. So grouping it's complicated already. Okay, oops, wrong. So the constraints you can imagine are a lot of constraints. Number of orders by group, because if it's summer, You can put, because they have like a car like this one's on supermarket cars. If it's summer, you can put more orders. But if it's winter, you can put less because they occupy more space. Okay, number of work groups by preparation, number of employees, the number of employees, number of SKUs by group, due date are the special constraints. So there's a lot of constraints here. What we did again a grasp for initial solutions. So you can see what we do. This is a hybrid metaheuristic. We did a neighborhood is like a VRP moves, insert, so it's like a VRP, insert and move from other one. And the perturbation is picking from another location. Let me explain this. So what the warehouse has, so some warehouses have all white t-shirts here, different size, all black t-shirts here, different size. No, in the text don't have that. They have white t-shirts here, white t-shirts here, white t-shirts there, because that helps the routing. So it's what we call a chaotic warehouse. It's not classified by types. Okay, so that's what we did, and they were able to provide 25% more orders by hour. This is amazing. This is really, really amazing for them. Okay, so that's I can write the paper, and we are still writing the paper, but paper is very weak because this we cannot say, this we cannot say. So my no disclosure agreement was bigger than my project, but basically, okay. So that's what I wanted to say about this. Then there is this one. Yeah, I'm gonna go past this one. I will leave it for you to read. This is a bias random key, and this is the idea. So we did a lot of randomness. I told you about 2 types of randomness. So say you can completely random or choose limited like grass, limited one and choose amount, like limited the first 3 and then choose one random. Another way to do randomness is to use a skew theoretical distribution where you sort them by quality, the best quality to the worst quality, and you can select any one. So this one, the high quality has more probability to be chosen than the worst quality. So that gives also one step further to really improve the search, because you don't avoid the bad ones. Maybe it's bad now, but maybe in the future will be good. Okay, this is a little bit the idea that we are multi-start bias random heuristics. Okay, and the idea is to have bias random initial solution and even on the perturbation. Okay. So we can use it here and we can use it here. So for example, say like, I want to do one move on the perturbation, and I'm going to choose that move with the bias randomness. The best one to the worst one, I give more probabilities to choose the best, but I'm not avoiding to choose the worst. Okay, that's a little bit when I'm going to jump this. I want to go this one because I think this is going to be interesting. Now what we're working a lot is mixing simulation with the optimization. There's several papers already mixing this, so this is not original, the optimization, the simulation. But the way we do it, I think it's original. So I'll talk about before the travel time. So travel time is stochastic. We can go to the average, but is the average good? I don't know. Maybe the average is not good. Maybe you want to have more than the average. Maybe you want to have like a service level 80%. So think about, for example, inventory. Is that enough to have inventory, average inventory? I don't think so. Companies want more than 80%, 90%. And in reality, what they want to know is the cost of having more. Okay. So what we're mixing is the SimILS. There's several already, some already work here, so I'm giving you some already work. But the reality is that, okay, in computational optimization, we know how to solve deterministic problems very well. And then when they have stochastic, some people do it very well in simulation. But in simulation, they don't optimize in a normal simulation. They just simulate. So why not mix the 2 of them? Why not mixing these 2 areas, okay? So the idea is the following, is extending the iterated local search using simulation. So you have a data, for example, you have average travel times. You obtain your VRP solution with average travel times, and you get the solutions. get the solution for your trucks. Then you simulate. You make a simulation, and you see, okay, truck number 1, in 90% of the times arrives when the store is already closed. So this is not good. So I have to change this data. I have to force this data so I can change. So what I do here is that generate initial solution, do local search and simulate, get some statistics. On these statistics, I use them in the perturbation to change the data or the solution. Can change both. I do again local search and I do statistics. And I repeat this. So the simulation can give me, for example, the travel time. In 80%. So 80% of the time, my travel time is under this time. So I use both. Here, we use Monte Carlo simulation, very simple simulation, just to give a sense. We can do this. So an idea is to have, since in this case, it's stochastic data, we have several curves. We don't have one curve because the curves depends on the data. So we need to have several solutions to see one solution that is better, is good for every curve or for 90% of the curves. Okay, so we can have stochastic in objective function, for example, travel times. Okay, so we can have the statistics, but for example, we can have another one we call service level. What is our service level? For example, in inventory. What kind of, where should we, how many products we should buy to have in the warehouse? And we have served 90% of our customers. The 90% of our customers will be satisfied, not the average. And putting simulation here, this is a very simple simulation. It can give you how good is your solution. Look, we're always working with deterministic data, but our data can change and change in function of what we obtain from the simulation. So let me give you an example. Now I'm going to jump this one. It's very, give me an example. This is, remember I told you some home care. So we're talking about home care. One problem in home care is that this is nurses, basically nurses, is that in a city, the travel times are stochastic. The parking time is stochastic. Because if don't find, usually they go by car, if don't find a car, take that. And they have a limited time of working. Even sometimes the service time could be stochastic. Even here, in this case, we are ignoring. Just the travel time is stochastic. And some people are complaining because they say, okay, you go to an area where there's more traffic, and I have to work 8 hours and I'm working 10. And I cannot finish until, you know, I see all the people that I need to serve. Okay, so the routings is like in VRP. You have to just assign the patients to the nurse, assign the service. You can do extra hours, but there is a cost, so we want to minimize cost. Here, cost is the cost of the nurse, the cost of the car, and the extra hours. Okay, but the travel times are stochastic. So what we do, we do iterated local search. We obtain the routing, and then we check with the travel time. We have data from the travel time. We have historical data from the travel time. Google can provide that, and we check with the travel time what happens. And we want that 90% of the times nurses can finish the work within their working hours, not 50%, because at 50% with unions, we have a problem. So then we change the data, we change the routes such that at the end, when we do the simulation, 90% of the time, the route is good. That's what we're doing. We have only preliminary results here. Another one that we've done, I wanted to show you some examples. This is Seat Volkswagen. So it's a factory your Volkswagen they have in Barcelona. There was a PhD student who did this. He has what they call industrial PhD. So he's hired by the company, but he's doing the PhD. This is something that the government is supporting, is giving scholarships for that in Barcelona, in Spain, in Catalonia. Yeah. So what they have is that they have the warehouse. They have here the warehouse, and they have to supply the production line with small pieces, with the boxes with the small pieces. You know, if they stop the production line, they have in big trouble, huge trouble. So they cannot stop the production line. The idea is that since the drivers, this is not like e-commerce, so they cannot ask and the driver goes. So this route must be like a bus route. You stop here, you stop here, you stop here, stop here. You can go. We stop here, stop here, stop here, stop here. For several reasons, some engineer reasons, they're like bus routes. They cannot stop. But demand is stochastic because depends on the car. They are manufactured. Demand is stochastic. So we have to design the routes. Okay, I have to design the route such that here is 95% of the times there's no. The station does not get out of stock. Okay, but the routes must be stochastic, must be fixed. Why the routes must be fixed? Because they try to do it, and we try to convince them to do variable routes depending on demand. But then they said we tried this 10 years ago, and it was a complete disaster because the drivers don't know where to stop, how to stop, and it was a complete disaster. So they don't know. So now the future is to use automatic guided vehicles, AGVs, but even that they wanted to have like this bus. I said like, well, why don't do like depending on the demand? No way. I mean, they want to have this boost routes for them. So this is a little bit what we have done here, and the results is really, really. They have done much more distance, so the distance was smaller. There was less delays because if there is some, if the product finished before the route comes, they can ask for a special delivery, but that must be used very, very little. We reduce that special deliveries, and of course it's very high quality, and the load level of the trucks. So the trucks were loaded more, so we was benefits of that. For that one, we have publish some papers, but not the full results because also the company does not allow us. That's a problem when you work with companies. And finally, the MathILS that I explained before. I'm going to give you some examples here. The idea here is that, okay, this maintains all the same, but here we use a much better. In the perturbation, we can use a much better. For example, if your problem is very big, we can say, okay, where do I have more difficulties in this area? So I ignore all the other and just optimize this part. I can or even do like a relaxation. I relax some constraints, some variables, and I solve it automatically. Okay, so for example, if we have a TSP with time windows, you just forget about the time windows and use the Concord here. Then your time windows are a disaster. Okay, but then you can fix it here. Okay, that's the idea, and I like that idea very much. Okay, so this is the idea I've told to explain to you in the scheduling. Scheduling is quite interesting. Some of them use like the Concord to solve the TSP because how many, for example, a driver in Barcelona from Amazon, how many packages they deliver in the morning?
35.
He knows it. Okay? So a TSP with 45, it's not a big deal. It's not too big. With 200,
Not for Concord.
not for Concord. But it's, so the idea is that one, okay? So why do a metaheuristics if you can solve it optimality? So you can relax things here. So this is a little bit. Okay. And the idea is that apply the metaheuristic for the real problem and use everything we know from theory to apply it on the parts on the perturbation. There's a lot of work done on cuts, exact methods, very nice work. So we can do this. For example, as I told you for the set covering, if you have a set covering, you can, okay, you have all these possible combinations. You just choose some and optimize. You reduce the problem. You reduce the dimension of the problem. But you can solve optimally without any problem. Okay, but again, mistake. So we did this combining with stochastic problem. This is a project that I cannot tell the name of the company, unfortunately. Okay, so this is a two-stage stochastic programming problem, which is like this, okay? It's a e-commerce, it's a supply chain for e-commerce. You have to decide today where to locate warehouses. Your demand is stochastic. But the strategy is, this is very good for strategical decisions. Today you have to decide where to open the warehouses. But you can forecast your demand for the future, but you don't know exactly. So we have two sets of decisions. One are strategical, and then tomorrow I have my demand, and I have to decide how to distribute it. That's an operational decision. Okay. Each customer must be assigned to 2 or 3 warehouses, regular. So so there's 2 or 3 warehouses that served Cape Town. Okay. Why 2 or 3 warehouses? Because if you're talking online, there's so many products that you cannot store every product in every warehouse. It's impossible. It's physically impossible. Okay. So if you look at Amazon, all the products that are in Amazon are not stored, all of them, in all warehouses, all distribution centers in this case. So you have to assign. Why do you need to assign this? This is customer area. Why do you need to assign? For transportation, to hire on advance your transportation, to know what companies you can understand or can understand that region. Okay. So there is a strategical decision, long-term decision, then operational decision. And that happens now a lot. And here there's something I think I wanted to go more on strategical decisions, because the strategical decision operational research have not been studied a lot, more operational. So we have a strategical decision where to locate warehouse, and then operation decision. Every day you have to decide how to distribute. But you have to solve this problem, taking into account that in the future we have to solve this one. These two are dependent. Okay? So the idea here is to use the iterated local search. You can use the strategical decisions here, optimizing, for example, optimizing a local location problem. With some data, optimize a location problem. Location problems are not so complicated. You can solve it exactly. And then here, check every day what happens. Optimize every day. Okay, or vice versa. You can also do the other way around. Okay. So let me look at this problem. So this problem, what we have done is looking at the mathematical model, and we use the deterministic equivalent model. What is the deterministic equivalent model is the following. You can create different scenarios. So you do forecasting your demand, and you do scenario 1, scenario 2, scenario 3, scenario 4, scenario 5, scenario for all demands. And then you optimize the location of warehouse that is good, let's say this, for all scenarios. Okay. Of course, you can see that this is a huge mathematical model, because to be realistic, you need to have a lot of scenarios. Okay. So it's like, do the VRP, since you are familiar with the VRP, it's like, okay, so what is the traffic in Cape Town at 9 o'clock in the morning? And scenario 1, scenario 2, scenario 3, 10 o'clock in the morning, scenario 1, scenario 2, scenario. So let's do the routing now, optimizing such that it's good in every scenario. Okay, so this is the equivalent, but we could solve this for small instances. And then we did a mathematics simulated iterated local search. So we use the mathematical exact methods to solve the location. And then we use the SimILS to see how these locations are good or not for every day. Because every day you have to assign customers to the warehouses. Okay, so we have operations decisions. You look with operations decisions. We look on the heuristic, and the exact method solves the location for one scenario. So we use a little bit this idea, getting statistics here. Okay, is there any customer that could not be served? Because we have here service level. Okay. So the idea is to have the local search is very simple, and the location is open, close, assign, not assign. So these are simple decisions. And then you have a destruction, reconstruction phase in the perturbation. Destruct part of the solution and reconstruct. Okay, this is the solutions we have. This is from a benchmark. You see the stochastic programming, deterministic only solve up to a very small instances. When there is big instances, we could not solve it. And the results were pretty good with very good times. We got pretty good examples, okay? So we could even get some better results, okay? So this was inspired in a real commerce. We used this to approach SimILS with iterated local search with some deterministic equivalent, and we were working on really improving this methodology, especially because many decisions are strategic. Sorry, I have to decide today. And then what happens to the future? Every day I have to decide things, but how many cars I'm going to buy for Uber? But then every day I have different. So a lot of decisions like this, we want to improve this technique. Is still not working as we'd like, but some theoretics that we work in include this deterministic equivalent model. Here we're using with few scenarios, for example, use only a few scenarios and get the optimal solution for a few scenarios, and then see how they behave on the simulation, how they behave for more scenarios. Okay. And that's a lot of things that we are doing, also integrating with Lagrangian relaxation, multi-objective and parallel. To finish, give you some resources, which is, this is a open source from VRP from Anan, one of my colleagues from Brazil. He has everything open, so you can download it. It's work in VRP for me is the best. Much better than everyone else. Is really amazing. Here's some other resources for team-oriented problems, and just to give you 2 examples for resources that you can download without any cost. The conclusions, I was planning to do some exercise, which I'm not going to do it because it's time. I hope you like this metaheuristic stuff and this iterated local search. As I said, it's a tool, so having more tools is good. It's good. Use it correctly. In reality, I'm very happy because when I started this with Olivier and Thomas, we never thought that we were just having fun doing something that we thought it was interesting and simple. But I think people are commenting, and even there's some articles about metaheuristics in general, and people are commenting that this is very simple. It's simple to implement. So the basic one, you can implement it easily. It's very simple to implement. The results are becoming very, very good. So it's very robust. It's very modularity. So you can do some recover, like reusing some models. And it's really becoming very popular. So if you have any question anytime, if you want to come to Barcelona, anything, just ask. We don't have money like any other one in university, but we can always look for, now we have Zoom and all these things, so it's very easy to talk. So it's a great pleasure to work. Georgina was visiting me, which is very nice, with the Erasmus. So Erasmus is a good opportunity, and students can ask for more time. Georgina only stay 5 days, but students can ask for more time, and look for Erasmus because there is quite a good thing. Okay, thank you so much. You want to go? Okay, I'm around this until Wednesday, so you can ask me any questions, stop me anytime. Okay, thank you.
Yeah, they went on one side. Simple.